Dubai can turn the sea into drinking water, but the salt it removes does not simply disappear. Scientists have measured seasonal low-oxygen water covering an estimated 50,000 square kilometers near the bottom of the Persian Gulf. That does not mean Dubai created it, but the city is returning an enormous, heavy byproduct to the exact same Gulf on which its entire water supply and its economic survival depends. Is Dubai solving its immediate water crisis only by adding immense pressure to another one beneath the surface? And if this vital marine ecosystem reaches a tipping point, how long before the billion-dollar hospitality engine of Dubai grinds to a complete, desolate halt? This is not a story about a broken machine. It is a story about an engineering system doing exactly what it was built to do. But in the modern economics of extreme environments, the most dangerous failures are often the ones that operate perfectly, quietly shifting their consequences somewhere the customer cannot see. To understand the scale of the waste, you first have to understand the sheer desperation of the demand. Desalination is not a secondary utility in Dubai. It is the absolute, non-negotiable foundation of human existence in this environment. Without it, the city ceases to function within a matter of days. Look at the modern landscape of this emirate. We are not just talking about drinking water for apartments. We are looking at a hyper-developed hospitality sector. Consider the Michelin-starred restaurants that have recently landed in Dubai, the luxury real estate developments, and the sprawling manicured promenades of the Dubai Marina. These are massive operational engines that require astronomical volumes of fresh water to maintain the illusion of an oasis. But that illusion is experiencing a creeping market saturation, and the economic fragility of this luxury dependency trap is intimately tied to the volume of water the city can realistically manufacture. By the end of 2025, the installed desalination capacity of the Dubai Electricity and Water Authority, or DEWA, stood at 495 million imperial gallons per day. We refer to this as 495 MIGD. But look at the peak demand in that same year. The city required 487 million imperial gallons in a single day. To put that into a physical perspective, 487 million imperial gallons is enough water to drain nearly 900 Olympic-sized swimming pools every single day, just to keep the city from drying out. At peak demand, Dubai was already drawing dangerously close to the absolute limits of its installed infrastructure. The margin for error is razor thin. To sustain its growth, DEWA aims to increase its total desalination capacity to 735 MIGD by 2030. What makes this more unsettling than a normal engineering failure is that nothing needs to explode. The factories are modern. The pipelines are secure. The system works. But producing that volume of fresh water requires the plant to leave something behind. You cannot separate pure water from the ocean without fundamentally altering what remains. And what remains is the dark side of this construction miracle. When a city extracts the fresh water but leaves much of the salt behind, where do you think the remaining stream goes? To answer that, we need to look directly at the anatomy of the desalination process. We need to strip away the complex technical jargon and look at the physical reality of the water. Seawater enters the facility. Fresh water is carefully separated. A smaller, significantly more concentrated stream of water remains. That is the fundamental equation of keeping Dubai alive. Let us focus on reverse osmosis, the prevailing technology for new developments. Immense pressure is applied to push raw seawater through highly specialized semi-permeable membranes. The pure water molecules pass through the microscopic pores, destined for the city's taps, hotels, and construction sites. But the vast majority of the salt, the minerals, and the organic compounds cannot pass through. They are blocked, they accumulate, and they are concentrated into the remaining volume of water. This rejected water is known as brine concentrate, but it is not just salty water. Its specific characteristics depend heavily on several operational factors. It depends on the baseline salinity of the input seawater, which in this region is already exceptionally high. It depends on the operating temperature of the facility, and crucially, it depends on the specific chemicals required to keep the facility running. To prevent the delicate membranes from clogging with scale and biological growth, operators must introduce anti-scalants and cleaning agents into the system. These chemical traces do not simply vanish. They become part of the heavy, concentrated brine stream. So you have a volume of water that is significantly saltier than the ocean it came from, carrying traces of industrial operation, and often warmer than the ambient sea temperature. This is the unavoidable byproduct of modern survival in the desert. The plant has successfully extracted the commodity it needs to sell to the city. But the waste product must be disposed of. It goes back into the sea. But the Persian Gulf is not an unlimited mixing tank. It is a highly specific, highly sensitive geographic basin, and the way this brine interacts with that basin is where the physical risk begins to take shape. If you dump a bucket of salt water into the middle of the open Pacific Ocean, the vast currents and immense depths dilute it almost instantly. The Persian Gulf does not offer that luxury. We must look at the geography of this water body, not just as a location on a map, but as a living, active participant in this story. The Gulf is an extremely shallow, semi-enclosed sea. It experiences intense, punishing heat during the summer months, which naturally evaporates vast amounts of water, leaving it with one of the highest natural salinity levels of any marine body on Earth. Its only connection to the open ocean is the narrow Strait of Hormuz. Because of this restricted topography, the water exchange rate is agonizingly slow. There are coastal areas and semi-enclosed bays where the water simply does not flush out efficiently. Now, introduce millions of gallons of dense, concentrated desalination brine into this environment. In fluid dynamics, density is destiny. Water that is significantly saltier is heavier. When this dense concentrate is discharged from the coastal outfalls, it does not easily float or mix at the surface. If it is not rapidly and violently diluted by the outfall diffusers, this heavy stream tends to sink. It drops toward the seafloor and spreads out horizontally, forming what engineers call a negatively buoyant plume. Imagine a thick, heavy layer of liquid crawling along the contours of the seabed, resisting the natural mixing action of the tides. There is a valid scientific counter-argument here that we must acknowledge. Basin-wide studies suggest that the continuous outflow of deep, salty water through the Strait of Hormuz might prevent a catastrophic, unchecked rise in the average salinity across the entire Gulf. The system has a natural exhaust valve, but an average across the entire Gulf can easily hide what happens beside an individual outfall. The global average is completely irrelevant to the marine life trying to survive directly in the path of the discharge pipe. The design of the outfall, the local currents, and the specific underwater topography dictate whether that concentrated plume disperses or whether it suffocates the immediate area. The risk we are investigating is not a uniform blanket of salt covering the entire sea. The risk is an expanding network of intense, localized hotspots. And the first organisms exposed to these heavy, creeping plumes are not necessarily the ones that can swim away. When we talk about environmental burdens, it is easy to get lost in abstract marine biology. We need to ground this in physical reality. We need to look at who actually absorbs the impact when a dense plume of brine sinks to the bottom. We are focusing entirely on the foundational building blocks and the iconic residents of this coastal food web. We are not just talking about microscopic organisms in the mud. We are talking about the sprawling, vital seagrass meadows that act as the primary feeding grounds for the vulnerable dugong populations of the Persian Gulf. We are talking about the intricate coral colonies that provide critical shelter for endangered hawksbill turtles and Arabian carpet sharks. When a heavy brine plume blankets the seafloor, it introduces several immediate, localized pressures to these specific habitats. The first is severe osmotic stress. The sudden and persistent spike in salinity disrupts the basic cellular functions of these organisms. It pulls water out of their tissues. If the brine stream originates from a thermal desalination plant, it also brings a localized heat shock, pushing organisms beyond their thermal tolerance thresholds. Furthermore, the chemical traces we mentioned earlier can subtly alter the composition of the biological community over time. A triggerfish can dart away from a noxious current. A coral colony cannot. A seagrass meadow cannot simply relocate when the water around it fundamentally changes. And the dugongs that rely entirely on those exact meadows for survival cannot simply graze elsewhere when their feeding grounds become a hypersaline trap. They are forced to endure whatever flows out of the discharge pipe. We are not claiming that every single outfall creates an identical wasteland. The severity of the impact is highly variable. It depends entirely on the location of the pipe, the sophistication of the diffuser technology, the depth of the discharge, the strength of the local currents, and how close the outfall is to sensitive biological habitats. In areas with strong currents and deep water, the plume might dilute quickly enough to minimize the damage. But in the shallow, sluggish coastal zones, the dense water lingers. This brings us to a critical intersection of variables. If heavy, dense water remains stubbornly close to the bottom, resisting the mixing action of the ocean above it, it creates a physical barrier. It restricts the vertical exchange of water. Could this physical stratification make an already oxygen-stressed environment fundamentally more difficult to ventilate? If you seal the bottom layer of the ocean under a heavy blanket of salt, how does the seafloor breathe? At this point in the investigation, it is tempting to point a finger directly at Dubai and declare its desalination plants the sole architects of a marine catastrophe. It is an easy narrative. It makes for a great thumbnail, but it is scientifically inaccurate. We have to separate the verified data from the sensationalism. Extensive scientific surveys conducted between 2018 and 2019 confirmed a stark reality. There is a severe, seasonal depletion of oxygen in the Persian Gulf. Researchers measured significant hypoxia water with very low dissolved oxygen, primarily extending from a depth of about 50 meters down to the seafloor. This phenomenon typically begins developing in late summer and becomes most severe during the autumn months. During the peak of this hypoxic season, the area of low oxygen water near the bottom is estimated to cover approximately 5,000 square kilometers. The hypoxia is real, but the evidence does not show that Dubai created the entire zone. We cannot take the 50,000 square kilometer figure and lay it at the feet of a single city or a single desalination plant. The reality of the Gulf's hypoxia is vastly more complex, driven by a convergence of overwhelming natural and human factors. First, the summer seawater temperatures are extreme, which naturally reduces the water's ability to hold dissolved oxygen. Second, intense thermal stratification prevents oxygen-rich surface water from mixing with the deeper layers. Third, the natural decomposition of organic matter on the seafloor consumes massive amounts of oxygen. Fourth, the continuous influx of municipal wastewater and agricultural nutrients from surrounding coastal nations promotes eutrophication, turbocharging the biological oxygen demand. Where does desalination brine fit into this? Concentrated, localized brine plumes absolutely add heavy osmotic and physical pressure to specific coastal areas, but their exact percentage of contribution to the massive 5,000 square kilometer hypoxic zone remains fiercely debated and unproven. So, asking did Dubai create the Gulf's dead zone is the wrong question. It is a weak question that scientists will easily dismantle. The more defensible question is this: if the bottom of the Gulf already loses its oxygen during the hottest months, And if the ecosystem is already pushed to the absolute edge by heat and pollution, how much additional local stress can its coastal zones absorb before the foundation of Dubai's luxury tourism begins to fracture? If this marine ecosystem collapses, the ripple effects will not be confined to the water. And this is where the story becomes larger than Dubai. Dubai serves as the perfect, highly visible face of this investigation. It has a globally recognized skyline, an undeniable and growing dependence on desalinated water, and a booming economy built entirely on the premise that water will always flow from the taps. The connection between freshwater availability, luxury tourism, real estate expansion, and economic stability is starkly visible here. We can see the empty walkways of the Marina waiting to be filled, and we know exactly what powers them. But the dense salt water sinking to the bottom of the Gulf does not carry a passport. It does not only come from Dubai. The entire coastline of the Persian Gulf is lined with massive desalination infrastructure. A comprehensive global assessment published in 2019 estimated that Saudi Arabia, the United Arab Emirates, Kuwait, and Qatar together produced roughly 55% of the world's desalination brine at the time the data was compiled. More recent reviews from 2026 continue to estimate that the Middle East accounts for approximately half of all global brine production. This is a sprawling, decentralized industrial network. We are looking at multiple nations, drawing from the exact same semi-enclosed sea and returning their concentrated waste back into the same shared basin. There is no single pipe that can be shut off to fix the problem. The less sensational explanation may be the more troubling one. We are not dealing with a single rogue factory violating regulations. We are dealing with an entire regional economic model that systematically treats the seafloor as an infinite waste receptacle. We must view this crisis across three distinct levels. At the plant level, you have the immediate, physical damage of the dense plume suffocating the local habitat. At the city level, you have a relentless, compounding demand for more water to fuel hospitality and construction. And at the regional level, you have half a dozen nations collectively stressing a marine ecosystem that is already battling severe natural hypoxia. But Dubai cannot simply switch desalination off. Doing so wouldn't just cause an inconvenience. Removing the marine pressure would create an immediate, catastrophic water crisis on land within 48 hours. The luxury hotels would empty, the restaurants would shutter, and the economy would halt. So, if shutting down is impossible, can the city engineer its way out of the trap it built for itself? The engineering community is well aware of the brine problem, and solutions do exist. But the problem is not a lack of human ingenuity. It is an inescapable thermodynamic reality. Every engineering solution requires a severe trade-off. The first and most immediate solution is better outfall design. Instead of dumping brine out of a single pipe, modern plants utilize multi-port diffusers. These are underwater pipes, fitted with multiple nozzles that shoot the brine into the sea at high velocities. This forces rapid mixing with the surrounding seawater, breaking up the dense plume before it can settle on the seafloor. Engineers can also position these outfalls carefully, avoiding sensitive seagrass or coral habitats. But a diffuser only hides the problem more efficiently. It dilutes the salt faster, but it does not remove a single gram of salt from the ecosystem. The second strategy involves shifting the technology. Dubai is aggressively expanding its reverse osmosis capabilities, most notably with the massive Hassyan project. Scheduled for completion in early 2027, with a staggering design capacity of 180 million imperial gallons per day, this facility relies entirely on membranes rather than boiling the ocean. It uses significantly less power, reducing the carbon footprint. But mechanically, it still creates a dense brine concentrate that must go somewhere. This leads to the ultimate engineering holy grail, zero liquid discharge. The concept is beautifully simple. Boil and process the brine until literally nothing remains but dry, solid salt blocks. Not a single drop of liquid enters the sea. The environmental benefit is absolute. The limitation is brutal economics. Processing water to that extreme requires astronomical amounts of energy and massive financial capital. You also trade a marine pollution problem for a colossal solid waste disposal problem on land. You cannot simply assume this is an immediate, viable upgrade for a sprawling city like Dubai without shattering the current pricing model of water. Therefore, the most critical solution has nothing to do with the desalination plant itself. It is about demand reduction. It involves maximizing wastewater reuse, upgrading infrastructure to minimize pipeline leaks, enforcing strict water-saving technologies in every new luxury development, and fundamentally rethinking the reliance on water-intensive landscaping in a desert environment. We must adjust the demand rather than blindly expanding the supply. If eliminating the brine makes every single liter of drinking water substantially more expensive, should Dubai pay that price right now, or allow the Gulf to quietly absorb the impact over the next few decades? You either pay an astronomical premium in energy and infrastructure capital to destroy the waste on land, or you pay with the slow suffocation of your coastal seafloor. Let us return to where we started. That crystal-clear glass of water poured in a Dubai hotel. If you trace the water back through the pipes, past the city skyline, through the reverse osmosis membranes, and down into the discharge outfalls resting on the seafloor, the reality of the transaction becomes clear. The glass was never truly free. Part of its price was simply paid somewhere the customer could not see. When we evaluate the impact of this system, we must deliver a verdict across three specific layers. First, regarding the unproven, there is no evidence that Dubai alone created the massive dead zones across the Persian Gulf. To claim otherwise is a failure of factual investigation. Second, regarding the established reality, seasonal low-oxygen water has undeniably been measured near the bottom of the Gulf, and highly concentrated brine from desalination can absolutely create severe, localized environmental pressure around poorly diluted coastal discharges, threatening the very creatures that define these waters. Third, regarding the systemic risk, the real concern is not that one single pipe from one single city is killing an entire sea. The true threat is that a rapidly growing network of thirsty cities may be adding relentless, concentrated pressure to an ecosystem that already operates dangerously close to its biological limits. Dubai proved to the world that brute force engineering can turn the sea into drinking water and build a glittering economy in the sand. Its next test is exponentially harder. Can it produce that water without treating the Gulf as a dumping ground? If the sea dies, the city dies. A system does not have to break to fail. Sometimes, it only has to keep working perfectly, exactly as designed, while its devastating consequences remain quietly outside the frame. This video examines documented environmental risks and unresolved scientific questions regarding desalination. Conditions vary significantly between individual plants, outfall designs, and local marine topographies. Current scientific evidence does not establish Dubai or its infrastructure as the sole cause of large-scale hypoxia in the Persian Gulf. This analysis focuses on the broader systemic risks and localized pressures based on available data. Should concentrated desalination brine be strictly regulated, like heavy industrial waste, even if forcing plants into zero liquid discharge makes the cost of drinking water and tourism drastically more expensive? Tell us in the comments where you think the true cost should be paid, and subscribe for our next investigation into the hidden engineering systems desperately keeping the modern world alive.